Guess next up is Chad Hunter doing an introduction to industrial control systems.
Yeah. Um, so let me see if I can share my screen here. Let's see. Okay, I can't tell if you guys can see the screen or not.
I can see it.
Okay. Um, okay. So my name is Chad Hunter. I am doing an introduction to industrial control system networks with some emphasis on uh, security threats. Um, I work as a security analyst or worked as a security analyst for Portland General Electric, and previously I worked for Bonneville Power Administration. So I have a little bit of experience dealing with the subject. I hold all three of the SANS industrial control system certifications. Not that that means anything, but at least I studied enough to get those. So right now we're looking at a picture of the Purdue model, which is a conceptual model that breaks down how industrial control systems are supposed to be structured, or how they fit into a corporate environment. And this was originally a conceptual model for process automation, and it's been adapted over the years. But basically, at the top level, that's where your business functions take place. Um, and then the bottom four levels are the uh, actual industrial processes, the controllers, the supervisory systems, and then the zone supervisory systems, we'll call it. So it's a layered level. They break it down with firewalls and switches and routers. The idea is to prevent traffic from freely flowing from a more secure zone to a less secure zone. The industrial demilitarized zone that you see on there, that's commonly called layer 3.5. That's been kind of added over the years, and it's used to be that there was basically an air gap there. Now it's a demilitarized zone, and that allows you to share services back and forth between the industrial side and the corporate side. So what is an industrial control system? So these are the devices that act as the interface between the digital and the physical world. They operate on a feedback loop where a sensor reads a value. The value is forwarded to a controller and compared to the parameters that have been set by the operator. If they exceed the parameters in some way, then a command is sent back to the actuator to bring things back in line. Sensor reads the value again, and this just continues on an ongoing basis. You'll always get a little bit of overshoot where you'll go a little high or a little low. So these devices are constantly adjusting themselves, and that's how the process is regulated. And that's the entire purpose of an industrial control system, is to automate and regulate that process. This is an example of a feedback loop. The person up in the upper left corner is the operator, sets the parameters, programs them in through the HMI or the control system. The parameters are passed down to the PLC, the programmable logic controller, which then monitors the physical process, and you develop your feedback loop. And this is just a line drawing of that feedback loop. So some of the common components that you'll find in industrial control systems are programmable logic controllers, which are the white box. They are a computer-based modular system. You can plug in a multiple types of input and output modules. They read the values. It's usually a serial value that comes in, so it's a yes or a no, 2-wire serial. Some of the newer modules are TCP/IP based. The protocols are usually serial based, but they'll, as we move forward, they get encapsulated in TCP/IP. They are also coming out with newer protocols that are TCP/IP from the get-go. So you can stack these modules in a number of different ways. Then you get your feedback from your various stations on your line, or in a substation, the various relays, whatever it may be. And then, like I said, if you exceed whatever parameter you've set, then the action is taken to get you back in line with that. The black unit is a remote terminal unit. It basically does the same thing, but it's a little more specialized, and it acts as a communication link between supervisory systems and control systems. So it will pass the data on up to another system where it can be evaluated by operators or another program. Here we have IED. These are also just monitoring devices, but they generally only have one function. Like they're a protective relay, so that if you have a voltage overcurrent or a voltage undercurrent, it'll shut the circuit down, or in order to keep the electric grid in balance, they'll do phase measurements and pass that data on, so that you can spin up generators or increase load to get things back in balance. The blue device, that's a valve that fits on a pipe. It's instrumented with a sensor and an actuator so that it can be open and closed to adjust the flow of, that's probably water, but it could be gas, sewage, whatever. And again, on the side, you see the terminals where it would be connected back into the PLC or the IED in order to provide those measurements. Supervisory components, don't really have good pictures of those because basically they're just computers. So you have a human machine interface, and that is the monitoring station for the process. And it's usually a graphic display that presents what's going on in the process in a visual fashion, so that people can just walk up and look very quickly and see what's happening instead of having to look at columns and numbers or whatever. Historian, that's a database. The ones I'm familiar with are almost all some form of SQL database that stores historical data about the process. And then you'll have alarm stations, so that if things get too far outside the parameters, an alarm will sound and safety actions can be taken. Operator and engineer workstations. On the the Purdue model that we looked at earlier, those would be like at level 3. Those are where the actual programming of the devices takes place. And they use something called ladder logic, which is basically, or usually they use ladder logic. There are other languages, but it's basically like a line diagram that, again, it's a visual representation of what the process is supposed to look like, so that it's easy to look at and see what's supposed to be happening. Although they can get pretty complicated if you're not experienced in what you're doing. And then that will get converted into a series of values and pushed down to the individual systems, and that's how they get programmed. And then the final one is the safety instrumented system, and that did not show on that Purdue model diagram because that exists below everything, and usually they are wired separately and kept off the industrial control network and off the corporate network. They're their own separate thing for safety's sake. And we'll come back to that here in a little bit. So this is a type of, when you're setting your systems up, there are a number of types of standard layouts. This would be a process control system. You're controlling one process. It's very simple. So it's not distributed across a bunch of different buildings or a bunch of different campuses. So it's probably the simplest implementation. This would be a distributed control system, and the utilities I worked at, we have a number of those that are deployed. Each like generation facility has its own distributed control system. And there are a number of process control systems that are joined together and then controlled up at this top level here, where, you know, the process historical archive is that sort of thing. And that's usually a Windows domain that is used to control a number of separate process control units or process control systems. So you start building on top of your systems and it gets complicated. You also start spreading things out more and your communications become more complicated because you may have to bring in things like wireless or microwave radio. And you'll have multiple protocols where on the first one that we looked at, you may only have Modbus, which is a serial process or a serial protocol. On this one, you may have TCP and Modbus, or DMP3, which is another serial process, and Modbus and TCP. So it adds a level of complexity, or a number of levels of complexity. And then SCADA system. And SCADA systems can either be a number of widely distributed process control systems, or a number of joined together distributed control systems. Basically, it's your process spread over a large area. So all of those terms, though, are now starting to be used interchangeably. So you'll hear people talk about ICS and SCADA and DCS and SCADA, or all of that, all in the same breath, and they're talking about the same thing because it's all just merging together. And this is one of the reasons why industrial networking and industrial security is becoming such a big deal, and becoming actually one of the reasons it's so difficult to deal with is you're dealing with a lot of legacy equipment and a lot of legacy protocols, and building stuff on top of them and adding complexity and merging all this stuff together, and then trying to push all of that up to the enterprise network through through a firewall and a DMZ, and do it in a way that protects your data, but more importantly, keeps your process up and running without shutting down so you don't lose money, and do it all in a safe manner. And uh, so this addresses what I was just talking about a little bit. Some of the differences between IT systems and industrial systems, why they're different, why industrial security is difficult. Uh, you got difference in performance requirements. Industrial control systems are usually real time. They have you have to be able to react to shutdowns or other emergency conditions pretty rapidly. They have to be up all the time. You have to plan your outages like weeks in advance so that you don't cost the company a bunch of money. So things like patching becomes a problem because you can't just say, oh, we're going to patch and reboot. You have to schedule that, and you have to do it at a time when the monetary loss or the shutdown is acceptable to the company. The software changes, simple things like Windows updates are complicated because in a lot of cases, you don't actually control when you can update the software. You have to get clearance from the vendor before you can do it. And if you don't, then you void your warranty or you void your operating agreement with the vendor. And communications, like we said, older protocols, some of them are proprietary. And then one of the biggest ones is a lot of that equipment is old. A lot of stuff out there that's 15, 20 years. When I worked at Bonneville Power, we had a lot of stuff out there that was like 35 years old, and it's not going to be updated anytime soon. So patching and maintaining becomes a real issue. So that's part one of the presentation. I'm not going to go into like protocols and all that because there's so many of them and it'd take forever. But so before I move on, are there any questions at this point? Anything that I can clear up before we go on? Okay. So we talked about the differences between industrial control systems and IT networks. So now let's talk about some of the threats. So basically, the four threats that you're really concerned about, or that I, as a security analyst working in this stuff, is really concerned about on an industrial system are an insider that can be either malicious or someone just being careless, making a mistake, programming the wrong thing. Hacktivists who are trying to cause the company damage. Nation state actors that are trying to gain information or trying to utilize, trying to break in and maintain a presence so that they can utilize it for advantage in the future, or cyber criminals who are trying to get some sort of monetary payout. And of those, the nation states are the ones that are probably the most concerning, because they have the resources to really throw at the problem. Compromising industrial control system networks is not as easy as compromising an IT network in general. There's, like we said earlier, there's a lot of proprietary protocols, there's a lot of obscure equipment, network setups are different. there's a lot of times there are air gaps or interruptions in the network connectivity, things like that. So it makes it much harder for someone to compromise a ICS system. And so usually the ones who really have the time to dedicate to that, if it's a properly set up system, are nation states. And so they're the ones that I'm most concerned about. And honestly, on this slide, the biggest concern, the two biggest concerns, aren't even on the slide because they're not really cyber concerns. Number one, for at least the electric grid, is like squirrels or animals that short themselves out on some component and bring a substation down. And then this kind of applies to industrial control systems in general, and that's vandalism. It's far easier to take an industrial network down or take an industrial process down with vandalism than it is to do it through a cyber attack. So, so we're just talking about it's harder to compromise an industrial control network than it is an IT network. So here we see the normal cyber kill chain for an IT network. They do some reconnaissance, they find a weakness, they try and exploit that weakness, deliver the malware, exploit whatever they can, or deliver the malware via exploit, install the malware, and then do whatever actions they're going to do. Exfiltrate data, ransomware, whatever they're going to do. So that's their normal cyber kill chain. And the ICS side, you have the normal cyber kill chain, and then on top of that, you have a second stage that's generally required once you get into the ICS network, where you have to develop knowledge in the network, figure out what protocols they have, what equipment they're using, develop a payload, test that payload in some way, deliver it, try and install it. If it won't install, then you have to modify it, and then if you can successfully install it, then you can execute your attack. It's a much more lengthy process. You'll read about attacks on ICS networks where the attackers were in the network for years, or they worked on the malware for years. Stuxnet being one of them. And so for all of that, with that kill chain in mind, there have only been 5 definite, 6 maybe ICS specific malware variants that have been developed. First one is Stuxnet. Pretty much everyone knows about it. The theory is that the US and Israel started working on it in 2005. They deployed it. It got discovered in 2010 because even though they tried to very specifically target it to a specific site in Iran and to specific hardware running specific software and targeting specific variable frequency drives, it turns out that Siemens hard codes IP addresses, and so everywhere that malware got introduced, instead of deleting itself like it should have, it spread. Fortunately, it didn't do any damage anywhere but Iran. But if it had not been as tightly coded as it was, it could have. So it was used for Windows 0 days in order to introduce the malware. They believe that they used infected USBs that were given to or distributed somehow to scientists working at the Natanz facility to get it into the building. Once it was in and on the industrial control network or centrifuge control network, it was able to spread and it targeted the Siemens Step 7 software. Had 3 modules, which the worm, it would look, see if it was already installed. If it was, it would delete itself. If not, it would install itself and then look for other computers to spread itself to. Using the link file, it would hide itself with a rootkit, and then it would drop its packages in order to disguise what was going on with the variable frequency drives, and then cause the variable frequency drives to spin up on the centrifuges until they destroyed themselves. And it was pretty nifty for the time. It was as far as I know, it's the first recorded instance of weaponizing malware to cause physical damage. The next one is Havex. This was discovered in 2015, and it was distributed from I believe it was the Rockwell website, where people would go to get updates to their firmware or software, and the website was compromised. They disguised the malware as legitimate software downloads, and people would install it. It would scan for specific ports, so that they would know that Rockwell and Siemens equipment, Rockwell's or Siemens equipment was used on that network. Then if it was, it would install itself and map the networks. And it was mainly used for gathering information about the networks, but it had the capability of carrying a remote access Trojan payload, so that they could have gone further. It was mainly used in the US and Europe, and there were a number of industries that were targeted. Defense, I think, is defense and pharma are the ones that I've heard that were targeted the most, but I think there's some debate about how far it was actually spread in other industries. Black Energy, there are a lot of variants on this. Black Energy 2 was used in the US. They found it in some corporate networks in utilities in the Northeast. But Black Energy 3 was used in the 2015 Ukraine attack. And Black Energy has continued to evolve. Black Energy 2 had a dropper that would deliver the payloads. Black Energy 3 just directly installs the DLLs. It doesn't need the dropper component anymore. And I haven't heard of it being used recently, but it is still out there. Crash Override and Indestroyer, another target on the Ukraine. For some reason, the Ukraine and Estonia, I think it is, seem to get targeted a lot. Probably because, well, it's the Russians, but they kind of use them as their testing grounds. This was specific for the electric grid, and again, it was modular. This one was particularly nasty because it would wipe the hard drives on the systems, so that even if when they came in to restore service, they couldn't, because their control systems were wiped, so they had to revert to manual control on their substations and generation plants. And fortunately for the Ukrainians, they were well versed in that. But it was specifically designed to disrupt activity on the Ukrainian electric grid. So this is probably, it's either the last or second to last, because the next one people debate whether or not it's ICS specific. But Triton Trisus, this one was a really big deal because it's the only known attack on safety instrument systems specifically. And the Triconic safety instrument systems are, I think, the most widely installed systems in the world. This was designed to mimic the controller software, and they could either cause false readings or shut the systems down so that the plant would operate in an unsafe condition, or shut the plant down. And there was a real possibility of loss of human life, and that's why people were so concerned about it, because it really escalated the game as far as ICS malware goes. And then number 6, again, some debate on this one, is ECANs and or Snake, depending on who you read. But this is just ransomware that has been designed to specifically target, that can specifically target ICS systems. It can be used in other systems also, but it has a set of functions to specifically target ICS systems. Let's see. So, Andre, are these ICS air gaps passed by human error, social engineering, missing security patches? There's a number of ways to get past them. A lot of them are because air gaps are never truly air gapped. You have to move stuff in order to either add equipment or update software, or update the programming, or get data out. So you keep it as gapped as you can, but it's never 100%. So you try and be as vigilant as you can. I worked on a network where everything that came onto the network was very tightly monitored. And we even went so far as to set up systems so that if they detected an outside internet connection, and they would check like every 10 seconds, they would shut down all the network ports. But we would still occasionally get someone who would bring in an unauthorized USB key and plug it in, and we would get an alert, and we'd call and let them know, that we saw them. But then we got Conficker on the network, or almost got Conficker on the network. It was detected, and the system was isolated before it spread. But because we got an oscilloscope in that had Conficker on it when we got it in from the manufacturer, and that oscilloscope had to be used on the network. So it was used for maintaining equipment on the network. So there's a bunch of different reasons, but usually it's human error. I would say most often it's human error. Either somebody connects something, forgets to disconnect it, or they accidentally plug into the wrong port, or they forget and they put a USB key that shouldn't be on that network on the network. So yeah, I think usually it's human error. So anyway, ECANs, ransomware, they found it last December. It has to be launched interactively. It doesn't propagate, and the scary thing is while it's installing itself, it doesn't interrupt user access to the system. So there's no chance to isolate or to interrupt it before the damage has been done. And then finally, if you're in a position where you have to make some decisions on securing industrial control systems, these are the 7 steps that DHS recommends, and prioritized by effectiveness. I actually disagree with this a little bit, but whitelisting, I know a lot of people don't like that because it's difficult, but on ICS networks, you have a much smaller set of software and protocols that you're dealing with, or operating systems, that sort of thing that you're dealing with. So it becomes easier. Configuration and patch management. Patch as often as you can safely in order to keep your systems up to date. Reduce your attack surface. Segment your networks, and authentication. Now, this is one that I think should be a little higher up on the list, because every successful attack on an industrial network that I'm aware of has started out with some sort of credential harvesting, usually by social engineering. So if you keep people from using the same credentials on your industrial network as on your corporate networks, then you're going to get a big win right there. But that is hard to do because it inconveniences the users, and bosses don't like that. Secure your remote access and monitor. Again, this is a hard one because a lot of networks are pretty isolated, and so it's hard to get that information. But monitor as closely as you can and know what your normals are supposed to be. And if things vary outside those, then respond. And then this is just the sliding scale of ICS cybersecurity. And as you start over at architecture and move up, it's where you can get your easiest wins early on. The least effective win, or the least effective thing, is to do like hackbacks, which are way over on the right and up, up and to the right. And then these are the references I used. So if you guys want to look any of this stuff up. And any other questions? I don't hear any, so let's see. How do I stop sharing? How do I stop screen sharing?
It should just be down at the bottom. There's if
you're sharing, it's also on top in the middle. If you go with your mouse.
Let's see.
I just stopped you from sharing.
Okay.
Oh.
Thank you.
Okay, thank you very much, Chad. It was really good having you present on ICS. I know it's a topic that a lot of us don't know a lot about, but we know it's really important, especially in terms of cyber warfare. So I really appreciate you educating us.
Thank you.